Modern oil refineries process highly volatile hydrocarbons on a massive scale. To an outside observer, the systems appear designed for continuous, quiet operation. But when pressurized containment fails, that stored energy is released in an instant. Before examining these failures, a quick note. This video is for educational purposes only and does not constitute legal or engineering advice. A vapor cloud explosion occurs when pressurized fluid escapes containment. Hitting the atmosphere, it rapidly expands into vapor. If it pools in a congested industrial area, it mixes with ambient air to form a highly flammable cloud. When these vapor clouds ignite, the devastation is often incorrectly dismissed as an unavoidable accident. In reality, the physical explosion is just the final, predictable outcome of long-term failures in process safety management. In March 2005, the BP Texas City Refinery exploded. Later that year, the Buncefield Oil Depot went up in flames. And in 2019, the Philadelphia Energy Solutions Refinery suffered a catastrophic blast. Despite different locations, all three shared the exact same systemic blind spots. Many organizations track safety by counting slips, trips, and falls, what the industry calls occupational safety. Process safety is entirely different. It focuses on keeping hazardous materials and immense energy safely contained inside the pipes. To regulate this, the Occupational Safety and Health Administration developed Standard 1910.119, the Process Safety Management, or PSM, framework. It establishes 14 mandatory elements designed to prevent catastrophic chemical releases. When an organization prioritizes daily production targets over the physical reality of these PSM pillars, a loss of containment event becomes a mathematical certainty. The only question is when it will happen. This document is a section of the OSHA PSM standard outlining mechanical integrity. It mandates that critical process equipment, like pressure vessels and piping systems, must be continuously maintained and inspected using recognized good engineering practices. We can observe the physical cost of ignoring this pillar at the Philadelphia Energy Solutions Refinery. In 2019, a massive release of toxic and flammable hydrofluoric acid vapor destroyed the facility. The rupture occurred at a single carbon steel pipe elbow, installed back in 1973. It contained high concentrations of residual nickel and copper. In an HF acid environment, these specific elements cause the steel to corrode at a highly accelerated rate. Industry standards warned about this specific corrosion risk for decades, yet the facility's inspection program never included this aging elbow as a monitoring location. Hidden from view, the steel wall thinned down to just 12 thousandths of an inch, roughly the thickness of a credit card, before the operating pressure tore it open. The mechanisms of HF acid corrosion were well understood across the industry. Allowing critical equipment to run to failure in a highly toxic environment is a breakdown in safety execution, not a lack of engineering knowledge. Physical breakdowns are preceded by organizational ones. When modifications to equipment or daily procedures bypass formal safety reviews, a facility begins to normalize deviance. This investigation slide from the BP Texas City disaster points directly to a failure in the management of change process. The refinery authorized the placement of occupied contractor trailers directly adjacent to a high-hazard process unit without conducting a proper safety assessment. At the Buncefield Oil Depot, operators were supposed to monitor tank levels with automated gauges, but the hardware was notoriously unreliable. As this section of the investigation report details, supervisors resorted to setting an ordinary alarm clock to estimate when the tanks were approaching full capacity. The Buncefield facility regularly passed its independent audits. However, as the final report concludes, those audits only checked if safety procedures existed on paper. They failed to test whether those procedures were actually used or effective in the control room. Management at both sites accepted these degraded systems and workarounds as standard operating procedure. That systemic blindness removed the secondary layers of defense that could have caught the initial errors. At BP Texas City, the sequence of failure began in a raffinate splitter tower. During a morning startup, operators pumped flammable liquid into the column. The level indicator was improperly calibrated, and a redundant high-level alarm failed to sound, allowing the tower to severely overfill. This flow diagram maps the subsequent chain of events. The overflowing liquid pushed out of the tower and filled an obsolete 1950s-era blowdown drum. Moving down the sequence, the obsolete blowdown system had never been connected to a flare, which would have safely combusted the excess hydrocarbons. Instead, it vented a geyser of hot, highly flammable liquid and vapor directly into the open air. The heavy vapor cloud drifted across the grounds, reaching the improperly sited contractor trailers. A nearby running vehicle engine provided the spark, igniting the mixture. The blast killed 15 workers and injured 180 others. Massive plumes of black smoke blanketed the area for days, a sight that would be repeated months later at Buncefield. The vehicle engine did not cause the BP Texas City disaster. It was simply the final spark in a long chain of unchecked mechanical defects, ignored alarms, and bypassed management reviews. Rebuilding process safety requires action far beyond the control room. Following the Texas City explosion, U.S. Chemical Safety Board Chairman Carolyn Merritt testified that true safety culture requires corporate leadership to integrate process safety directly into their highest-level decision-making. Facilities must stop relying entirely on lagging indicators, like tracking minor injuries after they happen. They must implement leading indicators, measuring, for example, the exact percentage of time critical safety alarms are left in a non-functional state. Operators must strictly adhere to recognized and generally accepted good engineering practices. When metallurgical science uncovers new risks, facilities must proactively update their inspection schedules to locate and replace legacy vulnerabilities. Ultimately, physical barriers mean very little without an organizational culture that supports them. True process safety exists only when every operator has the explicit authority and the management backing to halt operations the moment a safety barrier is compromised. Major hazard sites cannot afford to balance catastrophic risk against short-term financial gains. The commitment to maintaining the integrity of the process must be absolute. Vapor cloud explosions don't start with a single dramatic failure. They are the result of many small PSM deviations that go unaddressed. If you want to learn more about process safety management, refinery safety, and preventing major industrial incidents, subscribe to the HSE Study YouTube channel. Select one of the videos on screen to continue learning.